Hello. So in this lecture, we're going to show how the monotone convergence theorem can be used to establish the convergence of a given sequence. More specifically, we're going to look at how we can use it in determining the convergence of an inductively defined sequence, or in other words, a recursive sequence. So let Y be defined by y1, the initial term being equal to 1, and then yn plus 1 equal to 1/4 of 2 times yn plus 3 for all natural numbers n. So this is an inductively defined sequence, or recursively defined sequence, same thing. And our goal will be to show that yn converges and to also find its limit. Okay, so in order to do this, as I hinted at the beginning of the video, we're going to want to use the monotone convergence theorem. In other words, we want to show that yn is monotone and bounded and thus convergent by that theorem. So if you look at the first few terms of the sequence here, you'll notice that, well, I'll just write it out. Maybe first, notice y1 is equal to 1, y2 is equal to 5/4. And so y1 is less than y2, which is less than 2. So just observing these first two terms in the sequence, our hope would be that the sequence y is monotone increasing. And we know our hope would be that it's also bounded above. And 2 seems like a likely guess for that bound, just based off of looking at the first two terms of that sequence. So let's first establish whether or not the sequence is bounded above by 2, and then try to see if we can prove that it's monotone increasing. And once we have that, we at least have the convergence of that sequence. So let's go ahead and do that with a series of claims. So I'm going to claim maybe A. And this is a guess at first, and we'll figure it out once we get there. That the terms of the sequence are at most 2 for all n. Seems like a reasonable guess just based off of those two examples, I suppose. Maybe we should calculate a few more, but those two seem good enough to me. Okay, so now we're going to prove this claim. Proof of claim A. So the way that your textbook shows the boundedness of this sequence is by induction, and I would assume that a lot of textbooks would do it by induction. It's kind of a standard thing to do. You have like automatically a base case here, and then you can somehow use that to get the boundedness of the sequence. But I thought that this would be a good time to illustrate another proof technique that is less common in undergraduate courses, but I've used quite a bit in grad school or in my own research. And that is of a minimum or minimal counterexample. So what we're going to do to establish this is we're going to suppose by contradiction that it's false for some index. some natural number is going to break that bound. And notice that it's that natural number that breaks that bound can't be 1 or can't be 2 because both of those are less than it. So it's some number bigger than 2. And there could be many of them, but they're just natural numbers, and natural numbers have an ordering on them, which means that there's a smallest index that breaks that bound if you assume that it's false, right? So that's what we're going to do. So I'm just going to go ahead and state that. So by way of contradiction, suppose y of n is greater than or equal to 2 for some values of n. And again, these are just natural numbers, right? And then maybe say, and let k be the smallest such index. Okay, now just to like clarify it again with writing to the reader, I'll add an extra thing and say maybe like that is if n is less than k, then it doesn't break that bound. And yn is less than 2, and of course, y sub k is going to be greater than or equal to 2. And then just to note, k is greater than 2 itself. Oh, that's kind of confusing. K is just an index. We can just say it is definitely greater than 1 because y1 is equal to 1, so we know that that index that breaks it can't be 2 would have also worked, but I didn't want to confuse any of the viewers from thinking that this had anything to do with the sequence term. This is the index term. Okay, so we know this, so we can say maybe then, maybe, if yk is greater than or equal to 2, what is yk defined as? This, right? So then 1/4 of 2 times y of k minus 1 plus 3 is greater than or equal to 2, which implies that multiply both sides by 4, you get 2yk minus 1 plus 3 is greater than or equal to 8, which if you solve for yk, this implies that yk minus 1 is greater than or equal to, so 8 minus 3 is 5 halves. Which that itself is greater than 2. So this is the important part. Look what we've just found. We've just, under this assumption, shown that yk minus 1 is also greater than 2. But that's a contradiction because k is the smallest index that satisfies this bound. So like again, if any number less than k, y evaluated at that number is less than 2. That was our assumption. If we assume that this is false, we can look at all the indices where it's false. There is some smallest one. We call it k. But then if we assume that that breaks at that k, we get that y sub k minus 1 is also greater than or equal to 2, or greater than 2. So that's the contradiction. Let's write it down. Contradiction, since k was the smallest index with yk greater than or equal to 2. All right. So that's our contradiction. It's the smallest, but it's not the smallest. Can't happen. So when you prove claims inside of a proof, which is that's what we're doing right now, you put a little QED box here and then just circle it like that. Just so the reader knows the parentheses around the QED, it's a proof of this claim, not a proof of what we started at the outset. Okay. So now our hope is to show that it's monotone increasing. Okay. So that'll be my next claim. So claim B. Y of n is less than y of n plus 1 for all natural numbers n. Okay, and that seems like a reasonable guess based off of the first few terms here. So in the proof, if it's not true, we'll discover it. If it is true, we'll prove it. So here's the proof of claim B. And we can prove this by induction relatively fast, so that's what I'll do. Maybe we can say, notice y1 less than y2. We already observed that, right? Notice this satisfies a base case for induction on n. Right? We're trying to prove this true for all natural numbers n. That's the very first term, so that's our base case, which is nice. So now we need to assume our inductive hypothesis. So for our inductive hypothesis, you can see that. Suppose you can still see that. Good. Suppose that yk is less than y of k plus 1 for some k that's a natural number. Okay. And now we want to show that this implies that yk plus 1 is less than yk plus 2. Okay. Which is actually relatively easy by the way that the terms here are defined. So then, under this supposition here, yk less than yk plus 1 implies that if we add 3 to both sides and multiply 2 by both sides, we get 2yk plus 3 is less than 2yk plus 1 plus 3. Okay, which in turn implies that if we take a fourth of both sides, we get that y of k plus 1 equals to 1/4 of the left side is less than 1/4 of the right side. And the right side is equal to y of k plus 1. Okay, and that's it. That's what we wanted to show. Oh no, sorry, k plus 2, right? Because the k plus 1 term is there, and by the way that the sequence is defined, that's what it should be. So hence, y of n is less than y of n plus 1 for all n that are naturals. All right, so this is good. Oh, I forgot my little small QED. Okay, so we have that the sequence is bounded above, it's bounded, and then it's monotone increasing. So I can say claim A, comma, claim B, and the monotone convergence theorem imply that the sequence Yn is convergent. So this takes care of one part of what we were asked to do. We were asked to show that the sequence converges and then find its limit, and it is convergent by the monotone convergence theorem. We just had to establish first that it was bounded and monotone increasing. Okay, so now what's left for us to do is to find its limit. Obviously, I don't have any room left. So let me finish off a sentence here, and then I'm going to erase this board. So we know it's convergent, so we can just say, let y equal the limit of the sequence. And now we're going to solve for y. So let y equal one in the sequence and observe maybe. That y is equal to the limit of yn and y is also equal to the limit of yn plus 1. They're the same sequence, so they're going to converge to the same thing eventually. Okay, so now we just need to look at the structures of yn and yn plus 1. We can say maybe like this. The limit of yn plus 1 on the left-hand side of how it's defined right there is equal to 1/4 of, we have 2 times the limit of yn plus 3. But this implies that y is equal to 1/4 of 2y plus 3, which in turn, what do we have here? So 4y is equal to 2y plus 3, which means that 2y is equal to 3, which means that y is equal to 3/2. So what was y? That's the limit. Okay. So it follows that the limit of this sequence yn is equal to 3/2. Done. That finishes the proof of this problem statement. Okay. So again, what were the techniques that we used? We showed that it was bounded. Then we showed that it was monotone by induction. After establishing those facts, we state the monotone convergence theorem, which means that our sequence does converge. Under that assumption that it converges, we set a variable equal to the limit, and then evaluated the structure of the sequence and solved for that variable that we introduced. Okay, so hopefully this was clear and also enjoyable. I find these types of proofs fun to figure out the pieces and make them as nice looking as possible. And that'll be it for this recording.